piecewise functions. And I'm about to show you how to do it because I felt that guilty about saying, nah, you go and do it. And I'm going to explain it, and then you're going to look at it and you're going to say, I think I can explain it better. And if you can, that's great. I would love to see it. Right. I'll make this a little bit bigger so you can see the instructions, and I'll shrink it back. If you want to do a piecewise function, you do this guy, colon, and then what the function is going to be. So this would be for x less than 1, y equals 2x minus 1, which is basically that red straight line. And if you want to do, the other side, x greater than 1, you do that. Now, if you look at this picture here, do you see that there's no little circles or dots? So the only way I've figured out how to do that is to say, okay, that guy there at the end of the blue is at 1, 2. So you go 1, 2, and you plot a dot. And then you hit enter, and you go down here and you do, what's this one? 1, 1. And whoops, I forgot my 1. 1, 1. And when I hit enter, you get a dot. Now, if you don't like the colors being green and purple, hit that guy. Now, what I've done is the left mouse point, the left mouse button, and I'm keeping it in that. And when that happens, I can now make that a circle and make that blue. Now, doesn't that look pretty? And this one here, let's suppose that should have been a solid dot, but I would like it to look red because it just looks better red. There you go. There, can you see I've now made a very nice looking, I think, piecewise function. Don't know what happened there. Go away. There we go. Now, in this particular example, that's actually less than or equal to 1. The point is it doesn't do anything to the graph, even although you say it. You have to put the points in yourself and make them solid or open dots, as you can see here. Now that I've done that one, would you agree that one is a jump discontinuity? Isn't that one discontinuous at x equals 1? You can see all the usual kind of things. So has anybody found a better way? Because that's the way I found, but maybe you went online and saw an even nicer way of doing that. Anybody seen another way that you might think is easier for everyone else to do the piecewise, or does that kind of look like it? Okay, that was just a little side issue. Let's get back to the fun. And where the heck were we? We've done continuity, we've done left and right continuous, we've done questions where it says tell us the points where it's not continuous. What else have we done? Oh, we are now going to do, if I can find this. Right. We're now going to do questions about the domain of a function. Now, to remind you from 141, what the domain of a function is. The domain of a function, y equals f of x, is all usable values of x. That's an English definition. So if I give you a function, like this fella. Would you agree that this function only can be evaluated for everything except for one value of x? What would be the bad value of x in this function?
2.
2. So if you were trying to describe to people the domain of this function, you would say the domain is all real numbers. I'm doing it in English again. except for x equals 2. That makes sense. Now, if you wanted to write down the domain using what's called interval notation, you would do this. From negative infinity curve to 2, a union symbol from 2 to infinity. Do you recollect doing domains written like that? When you see a curve bracket, doesn't that mean you can't use 2? And doesn't infinities, plus and minus infinities, don't they always have curve brackets, right? There's just no way around that. So let's make a more difficult question. Where does this function have problems? What's the 2 places it's discontinuous? See, we're bringing in continuity now. Because there are 2.
3 and negative
3 and negative 3.
Agreed. So you could say in English, the domain is all real numbers except for 3 and negative 3, but we're not going to do it in English. We're going to do it using interval notation. So you go in negative infinity to negative 3, union 3, negative 3 I should say, all the way to 3, union 3 to infinity. Wouldn't that represent all the numbers except for 3 and negative 3? It's a little bit clunky, but that's how you write it down. Are we comfortable with interval notation for situations like this? So far, so good. Do you notice that the top doesn't matter? Couldn't the top be x minus 50, 42, or a billion x minus a half? Doesn't the numerator, the top of a fraction, have no effect on the domain? It doesn't, and it doesn't even matter if it cancels with the guy in the bottom. It's still a problem, right? Whatever gives you a problem in the bottom can't be eliminated, right? As far as the domain is concerned, it's there, you can't do anything about it. So let's move up and do a version of this question similar to question 16. And just because they can, the variable is now going to be called v. Now, if you want to answer this type of question, you know, what's the domain? You really need to factor the bottom. Don't worry about the top. It can be as ugly as you like, just ignore it. But I need to factor the bottom. And so you need to figure out what the 2 factors in this case are going to be. I can tell you right now, because that's negative, one of the numbers is plus and the other's minus. That's not much of a hint, but it's something.
X plus 9, x minus 4.
Okay, if you FOIL that out, don't you get it and it works, you're good to go. So in this question, isn't there a problem at -9 and another problem going to happen at 4? So when we do the domain in interval notation, negative infinity to the small one, which is that guy, the small one to the second one, which is that guy, and then the same number to the end is that guy. And that would be your answer at the end. Are we comfortable about these domain questions? Can we move on? Right. How about this fella? There's a one and only one value of t that's going to make this impossible to calculate.
Is it 0?
Excuse me. I'll be back in a moment. My apologies, I had something delivered that I had to sign for, so I knew it was coming, just didn't know when. Right, back to this question. There is a problem with this function. One value of t is going to screw it up. That's where we kind of left that.
The 0?
It is. Because aren't you really trying to figure out what makes up, right? And if you do that, I guess you've got that, and do you see t equals 0? So can you imagine in that case what the domain would look like? Everybody but don't use 0. Different situation. L of V. You know that's going to be my dog's agitated for the next 20 minutes because something happened and now they have to tell me about it. Okay. Hey, quiet. This one is not a fraction, but there are values of V where this function is going to have some problems, and it's more to do with usable values of V rather than infinities happening, directly at least. Right, we'll take it in slow stages. If you sketch the log function, okay, I'll call it what? Okay, we got it. You've told us the house is protected. Good boy. That's it. Would you agree that the log function only exists for positive numbers, right? You can't find a log, the natural log, in minus anything. So I am having to figure out when that is true. You can't use 0 because the answer is negative infinite. Now, there is a range of values of V where 1 take away V squared is positive. What is the range of values where 1 take away V squared is a positive number?
Is it anything less than 1? But greater than,
Less than 1.
-1.
There you go. Now, in this case, this actually represents the guys you can use. You notice in the other questions, we went hunting for the ones you couldn't use. In this question, we're actually finding the guys that you can use. So if you were asked to write this domain down, wouldn't it be that? Now, I know that looks like a coordinate, but in interval notation, doesn't that mean all the numbers from -1 to 1, but don't use 1 and don't use -1? Oh, there's some cube roots there. I'm not going to do them. Are we good? Some of this is really 141, isn't it? Slight overlap. Hopefully you remember domains. And now we're going to go to a thing called the intermediate value theorem. The intermediate value theorem. And let's show you what the intermediate value theorem says. Suppose you start at x equals a and you finish at x equals b, and you have a continuous function. At least from a to b, it's continuous. So it goes like this, it goes up, and it finishes like that, right? That would be your continuous function. And you have a guy here who's f of a and a guy at the end who's f of b. The intermediate value theorem, IVT for short, says the following. There must exist at least one value of x. We'll call it C. in the interval from x equals a to x equals b that has the property that f of c equals L, where L is any number, this is very wordy, in the interval f of a to f of b. Good grief. It actually makes a lot more sense when you see numbers. So imagine I have a function that starts at 1 and it finishes at 3. And the value of the function at 1 is 10. And the value of the function at the end at 3 is 70. The intermediate value theorem says you can pick any answer between 10 and 70, right? That's the L guy. Any answer you like. For instance, couldn't I pick 55? And it says there's guaranteed to be at least one number in the range 1 to 3 that has the property that f of c is 55. Does that make kind of sense that if you're a continuous function and you start at 10 and you finish at 70, don't you have to pass through all the numbers between 10 and 70 if you are a continuous function? Does that make sense? And maybe it's so obvious now that you say it. It looks a little bit wordy if you write it in English, but that's essentially what it says. Any questions about that? I'm taking that silence as good, but sometimes it isn't. So a question that uses the intermediate value theorem was question 20. And they don't make it obvious that you're using the intermediate value theorem. They ask you to show that there must be a root, right, a solution to this equation for x somewhere between 0 and 1. So we're going to prove that that answer exists, right? And see if we can come up with it. So first thing you're going to do is you're going to take that and you're going to rewrite it like that. And we're going to call that guy f of x. Would you agree that f of x is continuous? Right, there's nothing weird going on. So I can do it. And in particular, isn't it continuous from 0 to 1, right? It's continuous everywhere, but for this story, it's between 0 and 1. That's like the a and the b that we've got. Now the value at 0 is -9. And the value of this function at 1 is what? E plus 8 times 1 take away 9. That's E take away 1. That's roughly about 1.712. So at A, it's negative, and at B, it's positive. Now, according to the intermediate value theorem, isn't 0 somewhere between -9 and positive 1.712? Would you agree 0 is an answer? So according to the intermediate value theorem, there must be some place where f of c equals 0. Agreed? So doesn't that mean that this has a solution? And that's the proof. Bit weird. And they don't even ask us to go finding it. But if I did want to find the solution to that, I couldn't do it algebraically. So let's just pretend they had a part B and they said, okay, you've proved that there is a solution somewhere in the range 0 to 1, but what is it? Well, I'm going to do Desmos on this guy. And let's show you how I would solve that equation. So I go to Desmos. I could do it two different ways. The first way I'm going to do it is actually probably the easiest way. I'm just going to go e to the power of x, add ax, take away 9. Now, if you look over here, it's not a very interesting curve. Can you see it? If it's 0, it's 0 there. Can you see it? It says 0.836. Do you see that, guy? I found a solution. It's at 0.836. Would you agree that's definitely between 0 and 1, like the intermediate value theorem said? And the intermediate value theorem said, first, there's a solution to find. Second, that solution has to be between 0 and 1. And lastly, if you use Desmos, you can even find out what it is, if you need it. And the reason all of that works is because it was a continuous function. If the function we got was, a piecewise function like a jump discontinuity, couldn't you have a hole in the middle where there was no answers? Right? You could, that's what is the problem. When it's continuous, you can't have gaps or holes. The answer has to exist, and then you can go find it in the usual way. And we're getting close to the end. I think we are. So I go to question 21, which is, I believe, the last question. So one more intermediate value theorem. Okay, it's called, the equation that we're trying to solve is that. And the interval is 0 to 1 again, because they have no imagination. And if I rewrite this as cosine x, take away x cubed and call it f of x, kind of like the last time, would you agree that the cosine of x minus x cubed has no problems, right? It's continuous. And it's definitely continuous from 0 to 1. And now you find the value of the function at 0 and the value of the function at 1. I want one of those two answers to be a positive number, and I want the other one to be a negative number, because if that happens, can't I prove that this is equal to 0? So the value of the function at 0 is the cosine of 0, take away 0 cubed, which is 1. And the value of the function at 1 is the cosine of 1, take away 1 cubed, which is really for a calculator. So cosine of 1, take away 1 cubed is a very tiny negative number. It's negative 0.00015. Oh, well, check that I'm in degrees, isn't it? And yeah, right. So is the answer in degrees? Is the question in degrees? The question is in radians, so I'm going to change this answer. And on my calculator, I'm just turning things into radians and do it again. And the cosine of 1, take away 1 cubed, is still negative, but it's negative 0.46. So positive, negative, by the intermediate value theorem, there has to be a place where this guy is equal to 0. And then couldn't you go over to Desmos and find out what that guy is? And I believe it ends up being 0.86. 0.87. Okay, so it's somewhere in that range, which is fine. I'm about to leave intermediate value theorem. Is there anything you want me to go over or explain? Okay. Our new section. And we're back to limits in section 2.6. Is limits at infinity. So we're going to be looking at limits that have an infinity in them in some way or other. We can catch one. Okay. In particular, the first kind of things we're going to look at are vertical asymptotes. So this is going to be limits where the answer is infinity. Now, we'll do them visually because they're easier to start with. I'll have an x equals -2. I'll have an x equals 2. And then I'll have an x equals 5. And we're going to look at the 3 major types of vertical asymptote shapes that you get. One of the vertical asymptote shapes that's very common, isn't it, where both sides zoom up to plus infinity? In this case, the overall limit as x tends to -2 of this function would be called plus infinity. You wouldn't even write the plus, you just say infinity. And then you might get a shape where the vertical asymptotes both point down the way. And in that situation, the overall limit as x tends to 2 of this function would be -infinity. And then you can get situations where on one side it goes up, but on the other side it goes down, right? Isn't that also a possibility? And in that third and final situation, because that's basically all the shapes that you get with vertical asymptotes, it's a 5, isn't it? Is or does an overall limit exist in this last situation? This one has a plus infinity, this one has a negative infinity, but what about this one? Does it have an overall limit?
No.
Correct. And we will say does not exist. Can't you have left limits and right limits as well? And we've talked about them, so I'm not going to do them right now. I'm going to introduce you to some weird names that you're going to hear me say. When I do vertical asymptotes, I make up names for the shapes. So here are my names. See the ones that go up the way, right? The ones that look like that. I call them volcanoes. So if you hear me talking about a volcano, have you got in your mind's eye what kind of vertical asymptote I'm describing to you? I just think a word like that just makes your life easier. Now, do you know the ones that curve down like that? The ones that go down the way, like this one? I call them holes in the ground. Right? So if I said, oh, I've got 2 vertical asymptotes, at x equals -2, I've got a volcano, and at x equals 2, I've got a hole in the ground. Have you already got an idea roughly what that thing's going to look like, even although I've only told you it in English, right? That's what the words are, right? There's labels to help you. Now, this one here, where one goes up and the other goes down, I call them one of each. So if I say I've got a vertical asymptote and it's one of each, I'm talking about something like that, or the other way, right down the way and up the way. We good? So I'm going to change pictures for a second. And I'm going to draw some vertical asymptotes, and I'm going to tell you what I'm drawing, but you won't see it. And then I'll make it appear, and we'll see whether your mind's eye would be the same as mine. If it helps you, draw a little sketch of what you think I'm drawing, right? If it helps. So I'm going to have a volcano at x equals 1. So I've got a volcano at x equals 1. And at x equals -1, I'm going to have a hole in the ground. And this is me drawing it.
Are we supposed to be able to see you? Your
No.
share stopped. Oh, okay, sorry.
You're not meant to see it yet. Okay, I've now finished drawing this graph that has 2 vertical asymptotes. One of them was a volcano at x equals 3, and the second one was a hole in the ground at x equals -1, right? I've only used it in words, but you couldn't see it. Have you got in your mind's eye what that might look like? Right? Can you kind of visualize? Let's see if it matches what you thought. Is that what you kind of thought? Can you see the volcano at x equals 1 and the hole in the ground at the other end? Would you agree that's kind of what you would expect to get from the information that I gave you? Now, you don't really know what's happening here, but you get the gist of the shapes. So I think it's helpful. So I'm now going to show you a homework question. It's very visual. No way, I don't need to draw pictures. And we're going to look at just vertical asymptotes. So hopefully you are looking at question 1. Is that what you're saying right now? Okay. What is the overall limit as x tends to 1 here?
Infinity.
Yeah. X tends to almost said the answer there. X tends to 3. Overall limit as x tends to 3.
-infinity.
Right. Are you comfortable about pluses and minuses? If I'd asked you left limit or right limit, wouldn't you be saying plus or minus depending on the question? Great. Let's skip by that one. There should be another picture. Okay. Make it a little bit bigger. What is the overall limit as x tends to 0 in this one?
Negative infinity.
What's the left limit as x tends to 0?
Still negative infinity.
Right. What is, if it has one, the overall limit as x tends to 2?
Does not exist.
What's the right limit as x tends to 2?
Positive infinity.
Right. Are we getting comfortable left, right, overall limits, even when the thing's vertical, right? I'm pretty comfortable with those answers. They came pretty quick, which is a good sign you know what's going on. So let's show you another kind of asymptote, which I'm sure you've met before. Horizontal asymptotes. Right. You remember them from 141? Horizontal asymptotes. Let's remind you what that would look like. Let's put a vertical asymptote in just to muddy the water a little bit. Let's suppose at x equals 2, and then a horizontal asymptote at y equals, say that's 4. So you could have a shape that looked like this. And if someone said to you, the limit, the overall limit as x tends to 2 of this function, the answer would be it does not exist, agreed? The overall limit does not exist. If I went and asked you to find a right limit, which is written like that, you would say plus infinity. Now, if I ask you to find this fellow, the limit as x tends to infinity of this function, we are essentially saying as x gets bigger and bigger and bigger, what is the height? What's the y value that this is leveling off at? And the answer would be 4. Do you know that these kinds of questions don't have left and rights? Would you agree it's infinity and that's all you get? Now, in this particular one, you can also have a limit as x tends to negative infinity. And in my particular one, isn't it still 4? But can you imagine some questions where it levels off at 4 and then it levels off at 3 on the other side? So they could be different answers in different situations. So let's show you some weird versions of these guys. Do you see in this case, it's not a straight line, but isn't it kind of ripple that's dying away to almost nothing? That would still count as a horizontal asymptote, and the limit as x tends to infinity of this function would be 3. However, on this side here, the function just keeps on getting bigger and bigger and negative bigger and bigger. So if someone went and said to you, what is the limit as x tends to negative infinity of this function? Your answer will be negative infinity. Can you see why you would describe it in that terms? So not just horizontal asymptotes, we're now going to expand it to what the function's trying to do as x gets extremely big and positive or extremely big and negative. In this case, doesn't it flatline as a horizontal at 3, but in this case, it goes wild. So we've just adapted the thing to take other situations into account.
Would it be an oscillating function on the right side? And therefore,
Okay. Keep going.
and therefore, there was something about limits and oh, that was if it was a vertical. Okay.
I think I know
That
what you're
doesn't-
doing, and that's kind of interesting because the next shape I'm going to do is going to be that, and I'll show you what I'm talking about. Can you imagine you did a sine or a cosine function that oscillates as you describe it, right? If I said to you, what is the limit as x tends to infinity of this function? The answer is it does not exist. And it's not because it's oscillating. Would you agree this one's oscillating, but isn't it also dying away to nothing? So it's getting closer to 3. That's why this is 3. Isn't this never dying away? Isn't it always going to go up to 1 and down to -1 and up to 1 and down to -1? It's never going to finish its life anywhere in particular. That's what a DNE. Was that what you were thinking about, Rachel, when you're talking about oscillating?
I was thinking about the one that was, we had an oscillating one that we talked about as well.
Ah, right. And the one that we were talking about, if I remember, did something like this. That one. Is that the one?
Yes.
Yeah, and that has a problem, but it has a problem at the end. So in that case, the limit as x tends to 3 minus of the function would be does not exist. But that's not talking about, you know, the long term, what's happening over here, right? As the curve travels to the right. So when you do infinities, you're really saying, how does the function finish its life? You know, if x gets really big or negative, what does it do? And it sometimes becomes a number. and it sometimes doesn't exist, and it sometimes is infinite, right? That's the three kinds of typical answers that you would get. Okay, good questions. Let's return for the last few moments. While I'm doing this, will you say your last name for attendance purposes in the chat? Okay, here is that function again. What would be the limit as x tends to positive infinity? What is the limit as x tends to
2.
positive? 2, agree. What is the limit as x tends to negative infinity? Because it's not 2, it's a different number.
-1.
-1. You see that horizontal thing going on, even although it ripples a little bit? If I go to the one that's up here, maybe shrink it a little bit. What would be the limit as x tends to positive infinity here?
-2.
And as x tends to negative infinity?
2.
Do you see that flat line thing, as I call it? Oh, by the way, doesn't this shape have a volcano at 1 and a hole in the ground at 3? Isn't it a lot easier if I just use those phrases and, you know, try and, you know, add in vertical asymptotes at x equals 3 and things like that, right? That time? Yeah, that's time. Okay, perfect timing, everyone. You've got 2 minutes to spare. I'll hang about at the end if you have questions. Otherwise, I shall see you tomorrow. And we learned some cool stuff.
Thank you.
You're welcome.
Thank you. Goodbye.
Goodbye.
Thank you. Bye-bye.
Bye-bye.
Hi there. I had a quick question about was it
Uh-huh.
domains of a function?
Okay, well, have you got a question to go with it, or is it just a general question? What's it you want to ask?
Oh yeah, so on your notes that you had out there,
Oops, I just threw them away, but never mind. Keep going.
you were showing how to find the number that didn't work with it.
Yes.
I was a little confused with that. I was thinking that maybe just by the 2 problems you did, it was the perfect square of it. It didn't
No,
work.
there wasn't a perfect square.
It wasn't a perfect square.
No, if you thought that wasn't the main reason, even if it was, that wouldn't be the reason. So let me show you a quick summary of the situations. If it's a fraction, right? So if your function is a fraction like that, the places where you have a problem with a fraction are the places when the bottom, the denominator, is equal to 0. And in this case, when x is -3, that whole thing in the bottom is 0. And the other one is when x is -3, right? One is positive 3, the other is negative. So the domain will be everybody except those 2. So we would say the domain was up to, but not including -3, from -3 to +3, and then from 3 to infinity. So when the function that you're given is a fraction, factor the bottom and the places on the bottom which are 0, because when you factor it, it's easier to find those. Those are the places you can't use. In this case, 3 and -3.
Oh yeah, no, that makes actually a lot of sense. It just
Okay.
it clicked in my brain back from like pre-calc right there.
Okay, are we good with that now?
Yeah, we're good with that. I don't know. I wasn't connecting the dots earlier, but that makes a lot more sense now.
Okay, then I'll see you tomorrow. You can
Yeah,
always
thank
ask me
you.
again.
Thank you for clarifying that.
No problem.
Yeah,
You can ask me tomorrow if something else comes up.
you bet. See
Okay.
you around.
See you for